So, a significance test. A significance test is testing the evidence against a null hypothesis, or finding the probability known as the p-value. You guys have heard of a p-value, I think, most of you. Finding the probability that the results in your data occurred by random chance. Mm-hmm. And so Dylan ran a baseline calculation for his rock, paper, scissors, and he won a very low amount of the time. And we compared it to we compared it to just random results, and what we found out was it looked like it was low, but it was like there was a 13% chance. That happens like 1 out of every 6 times you play. Or 1 out of 7. It was about 1 out of 7, I think. So, yeah, that happens. Yes, it's not likely that he was going to repeat if he played again 50 times. It wasn't likely that he would do that poorly again. Sometimes you will do well, sometimes you do poorly. That's randomness. And that's an important thing to understand about randomness. Okay. So I'm a great free throw shooter. This is not talking about me. I claim that I can make 80% of my basketball free throws. To test my claim, you ask me to shoot 20 free throws. I only make 8. That's 40%. So you say someone who makes 80% of his free throws would almost never only make 8 out of 20. So I don't believe your claim. And you're going, no, I really am an 80%. I just had a bad couple of shots. So what we're doing here is developing a system to test, is that realistic? Was that if you really truly are an 80% free throw shooter, would you ever make this few? Well, the probability of that is it does happen, but it's 0.01% of the time. So I'm not really going to believe you. You shouldn't believe me that I am an 80% free throw shooter. I can shoot free throws, just not that well. There's plenty of people that shoot free throws in the 80 and 90%. A lot of them get paid to play basketball, but some of them are college students getting paid to play basketball. Okay, sweetening colas. Do you guys remember this example from 10.1? We had the sweetness taste testers, and we tasted the sweetness loss. And so this is with artificial flavor sweeteners. Artificial sweeteners tend to lose sweetness as they sit. And so they did an experiment and they did some things to make it age like it had been sitting for 4 months. And they tested the sweetness loss. And this is a matched pairs design. So the taste testers scored it before when it was fresh and then after letting it sit. And a positive value means it lost 2 on their sweetness scale. Means it's gained sweetness according to them. Now there's some random variation. Like even a trained taste testers, things taste different day to day. Yeah. I was like, yes, and yes, there are people that you go through some level of training, and yeah, your job is to test and sample things for food companies. Like Coke wants to know, is my Coke, Diet Coke, going to get worse over? And so, yeah, they actually, you have to train people so that if you just take randomness, there's way too much random variation. So these people should have a little less random variation, but yeah, this person thinks it gains sweetness. That's just part of it. So, but if you take a sample of 10, you'll get some level of normality and some, some level of their random variation. Well, one person will overrate the taste loss, probably, most likely in a sample of 10. So, giving you a mean of 1.02, the question is, does this mean it did lose sweetness? Is that enough to go to say yes? So we always have to start with a null hypothesis, and then we'll write an alternative hypothesis. You guys have heard that term? The null hypothesis is the no change case. A lot of times the null hypothesis is H naught that mu equals zero. The actual mean sweetness loss is zero. Okay. So the sweetness law, the population mean, if we did this with every possible taster, they would average zero. Uh-huh. And so what we're testing, and don't mistake significant variation for what this is testing is this random sample was essentially close enough that it would occur often enough, like that 13% of the time that we're going, actually, that happens semi-regularly. Like that happens semi-regularly. This isn't far enough away for us to say, no, this doesn't happen. This is probably different. And all you're testing is that it's different, not how different it is. Does that make sense? Maybe a sweetness loss of one, you're like, yeah, that's fine. That most people won't notice much of a difference, whether it's a month old or 2, 3, 4 months old. That this is an acceptable amount of loss. But what we're testing here is this enough to say it did lose? So my alternative hypothesis is that mu is greater than zero. We're assuming it doesn't gain sweetness. Effectively, my H naught is mu is less than or equal to zero because it's one-sided. We're just assuming that if it's less than zero, it's only random variation. That makes sense? So if it's truly zero, some of the random variation would be negative. That's a mu. HA, yes, alternative. H naught is H0. HA is alternative hypothesis. So H naught isn't always mu equals zero. So if we're doing SATs, the average SAT score is roughly 500 per section. You'd say H naught mu equals 500. Okay. When we're doing something like this where it's matched pairs, a lot of times H naught mu equals zero. But if it's not matched pairs, we're doing just one thing, we're probably not comparing it to zero. Okay. Where we'll get to by Thursday is two sample. Okay, where we've got two independent samples and we compare them, and that usually means mu1 equals mu2. Okay. The key though is H naught is the no change case, or whatever we would assume it would be. And that's harder than it sounds. It sounds really nice and easy. it's easy to get lost and miss that in the problem. It's always written in the problem. Practically speaking, you'll all probably do two sample if you're doing something with bio. So remember, we kind of had our four-step process, right? Remember that? Choose which one you're going to use. So this time we'd use a sample test, or this is called the z-test. We'll get to the t-test Wednesday. This is a z-test. The big difference is you know sigma. You must always test that you can. You're going to test. So part of step one is write your alternative hypothesis. Step two is confirm you can use the test. What are the things for the test? Not greater than 10. Um, that was for proportions. So for z tests or z intervals, has to be from an SRS. That's true for any one of these. This isn't a true SRS, but we're willing to treat our 10 taste testers as random taste testers. Yes. Yep. So does that make sense? We're not saying the general population of tasters, but we're assuming that our trained tasters are going to be better than the general population and have less randomness. And we're willing to treat the 10 we hired and their difference over this month as being random. That's a bit of an assumption that we can generalize this, but probably. Step two is normality. And with a sample size of only 10, we definitely need to do something to check for normality. Okay. They don't do it here. And they don't actually show you how to calculate this. But you get, for the 1.02, an X bar of 0.03, giving you a p-value of 0.17. So step three is you do the calculation. We'll do this in a second. And step four is, again, write the clue in the context.
What was step three?
Actually do the calculations, which I'm going to show you how to do by hand. Pretty much after today, you will not do any by hand. Okay. Step four is write your conclusion in the context of the problem. So it's helpful to write a stats conclusion. We either reject H naught. Congratulations. Congrats. So here's the key. We either reject H naught and conclude HA. If our p-value, so we've talked a lot about, we did 95% confidence level, right? 95% means p-value would be below 0.05. Okay? And we'll call this the alpha level. Whether it's 0.05, sometimes you'll do 0.01, that's like 99%. Or you might do 0.1 once in a while. But if it's below that alpha level, we reject H naught, conclude HA. If it's not below the alpha level, we do not conclude H naught. We simply fail to reject H naught. We don't have enough evidence that it wasn't random. It doesn't mean it wasn't true. It doesn't mean that the cola didn't lose sweetness. It just means it didn't lose enough for us to be certain that it wasn't random with this sample size. Okay. So that is an important distinction. We don't conclude H naught, we fail to reject. And then to put it in the context of the problem, I would say I don't have enough evidence to conclude that this cola lost sweetness from this test. That makes sense? I'm not concluding that it didn't lose sweetness. 0.05, it'll tell you in the problem if it's different. So if you're using something like in your bio IA, I would just say, I'm going to do everything at the 5% significance level. Like if you're choosing, just do 5% until you know better or have a good reason to know better. At the end of this, you might know better and have a good reason to know better, but you probably won't this year. And that's fine. I was like, I don't think the bio graders are going to grade you on, they're not grading you on your great use of stats. They're going to grade you on your conclusions. And being able to show that you understand some stats and learned it a little bit elsewhere wouldn't be a bad thing. I'm assuming the bio readers all know how to do the stats. So, outlining a test. Let's just go through one. Okay, they've got the null hypothesis. Studying job satisfaction. So, does job satisfaction of assembly workers differ when their work is machine-paced or self-paced? Do you guys know what that means? So machine-paced would be, this is coming to you this fast, you better get it together before the next one gets here. Self-paced would be they just give you the parts, you put them together. Okay, so you get to do it at your own pace, but machine-paced would be, well, you got it done, but the next one's not here yet. So one study chose 28 workers at random from a group of women who worked at assembling electronic devices. Half of the subjects were assigned at random to each of the two groups. Both groups did similar assembly work, but one work setup allowed workers to pace themselves, and the others featured an assembly line that moved at a fixed time interval, so the workers were paced by a machine. After 2 weeks, all subjects took the job diagnosis survey, a test of job satisfaction. They then switched work setups and did it again. So this is going to be a matched pairs again. And the JDS score, so we're trying to draw conclusions about all female assembly workers. We're not going to try to generalize this to male. Okay? Since the test was done on female assembly line workers. So step 1, H naught, mu equals 0. We're assuming there's no difference between the two. The alternative hypothesis is what we call a two-sided alternative. Mu is not equal to 0. We don't know which way is going to be more satisfying. You could assume self-paced, but maybe that's actually less. So we should check for not equal. With cola, if we expect this to lose sweetness, we don't need to test it. Oh, did it accidentally gain sweetness? And I'll tell you what you have to do different in step 3. So, I guess we don't have the data to actually run the test. Step 2 would be SRS. This is 28. They randomized, it's a matched pairs design, and they randomized who did which one first. So we're willing to treat that as an SRS. We'd have to check for normality. We don't need a lot of normality with n being 28, and we have to know the population standard deviation for z. Okay? As of chapter 10, you have to know the population standard deviation. By chapter 11, you could just use your sample standard deviation. The reason they do it in this order is because you already know how to run the z formulas. Okay? And there's some changes and complications. Most of chapter 11 and 12 are just building on this. They slightly change the formulas. Your calculator is going to do all of that for you. But the formulas change a little bit. A few assumptions change a little bit. But mostly what they're doing is, okay, here's harder scenarios. Apply that. Here's new scenarios. Apply it. Okay. The probability computed is going to be the p-value. So here we're calculating our calculation. Here's the first one. Okay, I'm going to show you how they did the calculation. And here's how they notated it. Your z-test, remember you had this formula, correct? Well, what you're going to do now is treat it like x bar is your mean. Mu naught is this mu right here. It's the mu from h naught.
So just zero, this is. Right.
Yes, it's mu naught. Square root of n, so that's sample size. So example 10.9, that was the job satisfaction one. It now tells me, nope, this must be the COLA sweetness loss. And now tells me it gives me an X bar of 0.3 and a sigma of 1. Point 0.3 minus 0 over 1 over square root of 10 gives me 0.95. And they're going to say P of Z is greater than 0.95. Probability that your Z value is greater than 0.95. So what we do with that, we go to our standard normal table, not the T one. Did I give you guys these?
Yeah.
Okay. I was like, I did print them. I know that. And remember, so I'm looking for the probability above based on how HA was. So I'm looking for this. That's equal to the probability below negative 0.95. So that I'm going to look up 0.95 in my Z table. That gives me the Z value. And so I would want to notate this Z equals 0.95. And that's why they're doing P of Z is greater than 0.95, which I think I'm going to just look up negative 0.95 instead of having to do positive 0.95 and having to do 1 minus. Does that make sense? and that's 0.1711. So my p-value is 0.1711. So I don't have enough evidence to conclude that this cola lost sweetness. It doesn't mean that it didn't. So I am failing to reject H naught. So that means I do not have enough evidence to conclude that the cola lost sweetness. I'm not concluding the cola did not lose sweetness. Do you hear that distinction? That is one of the hardest things in this. You do not want to say you've concluded that you don't. Effectively, yes, that means I'm probably concluding that I didn't. But I'm not ruling out the possibility of retesting it sometime in the future. I'm going to, and the closer it is to that 0.05, the more likely I would be to go, maybe we should test this again. A lot of times, what it effectively means is I didn't conclude that the cola didn't lose sweetness. I concluded that it didn't lose enough that I care. Like, I conclude that the amount of sweetness that the cola might have lost was not enough for the average consumer to know the difference. That makes sense. So there is definitely an I don't care that it lost that much. It's not significant enough. It's statistically significant, but we'll talk about tomorrow. Sometimes there's a difference between statistical significance and practical significance.
Wait, so p-value that is above the 0.05 threshold, right? That can still be statistically significant.
No, it's
Okay.
not statistically significant. It's not statistically. So that 0.05 is what we call the alpha level. You can have an alpha level of 0.1, 0.05, 0.01. It could be 0.02 as well, I guess. You can set the alpha level to whatever you want. We'll talk about different choices of that tomorrow and some of the consequences of that.
Like, should I state explicitly alpha level equals this, or can I just say the p-value threshold? That's what I said.
You should probably call it the alpha level or the confidence level. You might want to use the word confidence level.
Just do.
Yeah. Alpha level is the technical stats term. I think most like scientific papers are going to say a confidence level. So you can choose that, and depending on how sure you want to be, if you're like, well, we're giving out this new cancer drug, and we want to be sure that death isn't faster death is not a side effect, or maybe it's a weight loss drug. We want to be sure that kidney failure is not a side effect. You're probably going to use a 0.01 alpha level, something where you got to be really sure. If it's a cancer drug and you're like, well, this is for people that have terminal diagnoses and we might be able to get them 5 extra years instead of 1, you're probably willing to accept a lower alpha level. We don't need to be as sure because, well, if you don't take this drug, you're going to die. Yeah, but you're going to die soon. If you do, it might be later. So, okay. Does that kind of make sense on the significance level? It's a little bit of a weird thing, but yeah, this takes a little bit to get used to. Okay, so here's your 4-step thing. Um, one of the keys is identify the population of interest. You still have to say, identify what the population is, what you're trying to draw conclusions of. In step one, you state the null and alternative hypotheses. Step two doesn't change. Okay, I would say choose the appropriate inference procedure as part of step one, really, because you wouldn't write the null and alternative hypothesis for a confidence interval. So far, you have two procedures: Z interval, Z test. Okay. We will expand upon those procedures, but I would say choose the appropriate procedure. It happens before you would write an alternative hypothesis, but verify those conditions for the procedure you chose is there. That makes sense? If the conditions are met, you carry out the inference. If they are not met, because you are in a math class, you say, they might not be met, but I'm going to do it anyways. So this book calls that proceed with caution. If you're if you got hired out as a statistician, you would just go ahead and do the calculations anyways. Okay. But you would tell the company, hey, this might not be valid because you didn't actually do a simple random sample. You collected your data at the mall. If they did some other kind of good sampling method, if you're a statistician, you would know other tests for different types of samples. Systematic samples, like you chose every fifth person entering the school or something like that.
Determine that a sample isn't actually random.
It depends how you collected it. So if you just walked up to people at the mall and started asking things about things that are only semi-related to the mall, they're going to ask you how you conducted your sample. And then that's not random. Yeah, it's a convenience sample. If you say, I selected every fifth person that walked in the door of the school, I randomized to choose randomly picked which one was going to start with, whether it be the first person or the fourth person or whatever, and then did every fifth from that. That's called a systematic sample. And so they would go, that's not random. A statistician is going to have other types of tests for a systematic sample. It's going to be, I'm like, would that be different? Slightly. I'm like, that's only going to be slightly different. But if you collect your data in a way that is not going to simulate randomness at all, or if you collect your data every fifth person coming through the doors of Alturas and want to generalize it to high school students in America, I'm going to go, forget that. You just get to generalize this to Alturas students. Because, yes, you guys are not a great representative of all high school students in America. Yeah, hopefully you're better students. Hopefully you're also better students. So, and we are definitely not a diverse. So diverse, yes. Okay. Step three, calculate the test statistic. Test statistic means Z. Okay. In the next chapter, it'll mean T, which is effectively Z. In chapter 13, it'll mean the chi-square value. Okay. So test statistic is just the name for the value that we're calculating. And then you use the test statistic to get the p-value. And then step four, again, interpret in the context of the problem. Usually I encourage you to write a stats conclusion reject H naught, conclude HA, or fail to reject H naught, and give your reason based on your p-value. But then you must interpret it in the context of the problem. I think writing that stats thing will help you interpret it correctly. So I encourage you to do it. So let's carry out a whole test. No, we're not going to carry out a whole test yet. So we get a z-value of 1.7 on a two-sided alternative. So I'm going to do the negative 1.7 instead of the positive one. Negative 1.70. So notice they made the drawing here. Negative 1.7 is 0.446. No, 0.0446. So positive 1.7 is also 0.0446.
Where you would have to calculate.
What?
You would have to calculate like positive 1.7.
It's symmetric. That's why I've used the negative on the last one. So if I do positive 1.7, I can go to 1.7. And when I go 1 minus that, because that'll give me the left side, when I go 1 minus to get that right tail, it'll be 0.0446. So really all I have to do is look up the negative one and multiply it by 2. 0.0892. I saw that one before. So if your alpha level is 0.1, you can reject H naught and conclude HA. If your alpha level is 0.05, you cannot. And one of the things that's interesting with two-sided tests, if this were a one-sided test, it would have passed at 0.05. Is this any less valid because we chose to make it a two-sided test? Because now it's 0.0892. Not really. So a lot of times 0.05 on a one-sided test turns into 0.1 on a two-sided test. Does that make sense? Because that's 0.05 on each tail. A lot of times if you're doing a two-sided, it's okay to do an alpha level of 0.1. Not always. I think courts in America usually use 0.05 on tests.
Oh, course.
Court. Like if you're suing, the evidence that they're going to need to support them is 0.05. So here's your curves. Greater than, less than, two-tailed. So not equal case. You just double the one-sided p-value. Yep.
Is that all for their
Mm-hmm. H naught is always going to be mu equals something. And usually whatever that mu naught value is, you plug a number in for it. Whether that be 0 or 20 or 500 or... Okay, now we're going to carry out an example. Maybe two. So, the National Center for Healthcare Statistics reports that the mean systolic blood pressure for males 35 to 44 is 128, and the standard deviation is 15. Okay, The medical director at a large company looks at the medical records of 72 executives in this age group and finds that the mean systolic blood pressure of his sample is 126.07. Is this evidence that the company's executives have a different mean blood pressure than the general population? As usual in this chapter, we make the unrealistic assumption that we know the population standard deviation. So what we're doing here is we're assuming that the standard deviation of the executives at this company, because that's what he's trying to make conclusions about, is the same as executives nationally. That's an unrealistic assumption, but it's probably not a particularly bad assumption. Once you learn t-tests, we just do it with a t-test, but that's a pretty reasonable assumption that the standard deviation would be the same as the overall general population. So, identifying the population of interest. Step 1. Mu equals 128. We're assuming it's the same as the national average. Our population of interest is this company's executives 35 to 44. Okay, it's not all executives 35 to 44. We already have that data. We want to know if our company's different. So H naught mu equals 128. HA mu is not equal to 128. And notice how they're writing these out. The company's executive mean blood pressure is 128. The company's executive mean blood pressure differs from the national mean of 128. This is a two-sided, and notice how they wrote what those mean in words. That will help you with your conclusion. So I encourage you to do it, especially at first. Choose the appropriate inference procedure. Well, we're using a z-test. That's why we did this. Verifying the conditions for the mean. The data, it says, came from an SRS from the company. So we're good on that one. Of all 72 executives. We don't really need to check for normality because n being 72 is plenty large that my means should be normal by the central limit theorem. And 3, we are assuming sigma equals 15. So now we're going to run our test. Z equals my mean minus my assumed mean, or my H mu naught, for 72. And this equals negative 1.09. So my test statistic, as it's called, is negative 1.09. I shall go look it up in my table. Negative 1.09, 0.1379. I can write my test statistic here. It is a two-tailed, that was all our alternative hypothesis. So it's 0.1379. That means we're doubling 0.1379. Step 3 does get you your p-value. I'm just going to look back at what the book says to do that multiplication. 0.2758. So you always need to record this when you do your Should I reject or fail to reject H naught? So this is way too high to reject it, correct? So I'm going to fail to reject H naught. What this says is we lack evidence to conclude that this company's executives, male executives 35 to 44, have a different mean blood pressure than the national average of 128, mean systolic blood pressure. See all those details that I put in there? That tells you all the details, whether the person understands it or not. It was also very clear to somebody that doesn't know stats. This company's not different than me. You kind of aren't all there anymore. So, can you balance your checkbook? Is there any more after this one? Okay, let's do this one instead. No, you don't have to. It's really just an intelligence test. Let's go to the screen tension because we're running low on time. So you guys remember the video screen tension, right?
Oh, yeah.
So example, so the mean tension is 275. So we're going to test it at the 1% significance level. The mean tension is not 275. Alpha level is 0.01. So choose our appropriate inference procedure. Since sigma is known, we will use it. And Z, we tested this for normality in earlier. It passed, and this was an SRS. So we've met our conditions. So our X bar was 306.3, our sigma was 43. We want to be very sure that these aren't good before we throw them out. So that's why they're doing the 0.01. So we get 3.26. So we go to our formulas. I think this will pass. And again, I'm going to look up negative 3.26 because it's two-sided and I will have to double that. 0.0006. When I double that, that gets 0.0012. That is less than 0.01. So I will reject H naught and conclude HA. These are not good enough at the 1% level. Sometimes I still have to think about what I'm saying. It's the hardest part about this. So they've got a little bit more exact p-value because they used a calculator. So because of the practice of statistics, so usually you're going to use software to get that value. But yes, we're going to have to reject these TVs. The whole batch from this day. Sell them as seconds. Give them away. Take the screens out and use the rest of it. Okay. What you can sometimes do is, do you guys remember the negative 2.576 being the Z star for, remember that being the Z star for the 99% confidence interval? 0.01 is going to go with a since 0.01 two-sided goes with a 99% confidence interval. 0.01 one-sided would go with a 98%. So since we calculated 3.26, that's going to be outside of this 2.576. Which means, yeah, it's reject. Throw these out. And another way to do it is you can just test the confidence interval. This was our 99% confidence interval. 275 wasn't in that. You just have to be aware of two-sided versus one-sided. 0.01 for a one-sided test is actually a 98% confidence interval because it'd be 0.01 on each side. Okay. There is a connection between the two. You can use them both together. Okay, that is the introduction to this. Tomorrow we'll get into more of the details of what to use when, but all you need to do today is be able to perform a test, carry out the four-step process. Okay? Please actually practice this tonight. I know you have a bunch of other stuff to do, but please do some of these because tomorrow it gets more. And if you haven't practiced it, it's going to make tomorrow a lot harder.